Good morning, everyone. Let's get started. On Monday, we stopped at this page where we were talking about the motion of a charged particle into an electric field. And we stopped by saying that the horizontal motion of this charged object, is governed by its original equation, which we have from rectilinear motion, distance equal to speed times time. So at any particular point t, you can determine x. At any particular time t, you can determine the position since you know the horizontal velocity. And also it was coming horizontally before it entered this electric field, and that made it to start bending downwards. For the fact that it's bending downwards does not affect the fact that its horizontal motion is still governed by this expression, x equal to ux of t. And also, since it has entered this electric field, it started to bend downwards. And bending downwards, the motion is governed by this set of equations. So at a particular time, you can measure the distance y, the horizontal distance from its initial distance, because before it was coming straight, but when it got to have a pen, let's have color blue. Before it was coming in this direction, but on getting here, it began to bend downwards. So the t we have here was obtained from the t. From this expression, t is equal to x over ux, and then t square is equal to x square over ux squared. Then we have y. So let's move forward. So let's talk briefly on electric dipoles. When we talk about electric dipoles, we mean a pair of charges that have equal and opposite, that are equal in magnitude, but their charges are opposites. So when we say they are equal in magnitude, for instance, an electron is said to have 1.6 times 10 raised to power minus 19 coulomb as its charge. Similarly, the proton also has a charge of 1.6 times 10 raised to power minus 19 coulomb. That's those are examples of equal charges, but the charge of an electron is negative while that of a proton is positive. That means a proton and an electron have opposite charges. So when we have a system comprising of a proton and an electron, we can say that both of them can form a dipole. So when we have two charges, just like as illustrated on this page, when we have two charges, this is a positive charge and a negative charge. This is having a charge of Q, while the negative charge is having a charge of minus Q. So they are equal charges, equal in magnitude, but opposite in sign, opposite in nature. Both of them are separated by a distance A. So now, at a particular point P, so this system, the positive and negative charge, they form what we call a dipole, and they are separated by a distance A. So now we are interested, what happens at point P? What is the electric field at point P as a result of the presence of this dipole? Then we have to start by saying, okay, what is the distance from this point P to that dipole. So when the point of interest P is in between a distance y from the middle of both charges, then we can bring in Pythagoras theorem again. The distance between these points P and charge Q is R. The distance between the points P and charge minus Q is also R. And we can now bring in Pythagoras theorem to have a right angle triangle and to resolve a lot of things about the dimensions around Q in between A and P. So I don't mean to embarrass you, but when we say the points from this to this point, the distance between Q and minus Q is A, then the half here, the middle point here will mean A over 2 to the middle point here. The distance between K to the middle point here will be A over 2. And since the middle point here to the point P is Y, then we can have a relationship between three of them to say R squared is equal to A over 2 all squared plus Y squared. That's what Pythagoras tells us. And we should also note that in this, to bring in cosine of angles or sine of angles, we can, when we call this our theta, this angle our theta, then we should be able to also say that cos theta should be equal to, let me write it here. Cos theta should be equal to the adjacent here is A over 2 divided by hypotenuse. Hypotenuse here is R. And R is the square root of everything we have here. So looking at this expression and looking at this diagram, we can say that at this certain distance, at this certain point P, let's assume we put a test charge here. Our test charge is usually positive. When we put our test charge here, we would expect that this charge Q will repel it. So the electric field will act in this direction. Even when we put our test charge here, the electric field will act in this direction, which will give us this direction E1. And the second charge Q will want to attract the test charge towards it. So when you have one electric field pointing in this direction, the other electric field pointing in this direction, from what we learned about parallelogram law of vectors, then we can say that these are the, is it the principal sides of the parallelogram, or what do you call it? Okay, in short, this is the principal diagonal. These are the major sides of the parallelogram, and this is the principal diagonal. So the length of this principal diagonal will serve as the resultant or the vector addition of E1 to E2 will give us E. So we are interested in this E, and this E, it's you can see that E1, E, and E2, they are vectors. So it's easy to say that, to come with this first expression that tells us that E is equal to E1 plus E2. I hope this is not strange. We must have learned this in secondary school. E is the addition of E1 and E2, where we think of them as vectors, and we represent them as the sides of a parallelogram. The resultant will be E, which will be the vector addition of E1 and E2. That is E1 and E2 will give us E. So when we attempt to use our equations that we have known before about electric field, the equations we know before about electric field tells us that E is equal to KQ all over R squared. Now we know our K to be fixed. We know our R, the distance R between the point P to this, let's call this charge, the distance between our point P to this charge Q is R. The distance between this point P to minus Q is also R. So that means that for when we are trying to calculate what is the electric field E1 or E2, we should get the same, you should use the same R. And when we are talking about the charge, they both have the same magnitude. So we should expect that E1, in this scenario, E1 will be equal to E2, just like we have here. E1 will be equal to E2. So what is E1 and what is E2? E1 or E2 can be said to be K, just like I have here, just like I've written here, K equal to Q over R squared. And what is R squared? R squared, I've defined it earlier from Pythagoras theorem. That is everything on the right-hand side of this equation can replace R squared. Then we have this new equation. So coming back to the first equation that says E is equal to E1 cos E equal to E1 cos theta plus E2 cos theta. How did we get that? From that, our parallelogram law, we can, the angle theta here also is also applicable here within this parallelogram. So we can say that somebody is asking, how did you get R squared? R squared is from electric field, the formula for electric field strength, KQ over R squared. And we know the distance between these points. We are trying to calculate the electric field from this point P to charge Q and minus Q. So, and the length here is R. So, and from Coulomb's law, coming to the formula for electric field, we know that the distance is R, and we will need to say R squared. And why are we using cos theta and not sin theta? Cos theta is because it from Pythagoras theorem and basic trigonometry, cos theta is defined as adjacent over hypotenuse. And it is used when we are talking about right angle triangles. This is a right angled triangle. So, and this is theta, adjacent over hypotenuse. We are interested in adjacent over hypotenuse here. If we had used sin theta, it would be y over r. So it's for simplicity why we have chosen to use cos theta. And in this situation, when you look at this angle, E1 cos theta gives you E, because this is adjacent here and this is hypotenuse. This is like a vertical line here will serve as opposite, but currently this is our adjacent and this is hypotenuse. So that means that our E1 cos theta will be equivalent to E. So let's move forward, please. So, and similarly, E2 cos theta will also give us value of E. So when we add them together, we can have our 2E cos theta. And what is cos theta? Cos theta is, like I've defined before, A over 2, just like we have it, all divided by R. And this is R, which is obtained when you find the square root of this R squared. R squared equal to A over 2 square plus Y square is obtained by Pythagoras theorem. They taught me the Pythagoras theorem in primary school. And this is R, this is A over 2, and this is Y. So Pythagoras theorem tells us that the opposite square, so the opposite square plus adjacent square will give us hypotenuse squared. So let's move forward, please. Then coming here, we can now talk about this particular expression this particular expression is brought in here directly. So which tells us that the 2 here is the 2 we have here is right here, and E, which is equal to, which we've defined E to be KQ over R squared. This is the K, this is the Q, divided by, this is R squared. This is R squared from Pythagoras theorem, times everything we have here has been defined as cos theta. So when we simplify, we should have this final expression where we say this square root is as good as saying raised power 1 over 2. So with from basic mathematics, you can resolve and have this to be K. So from that expression, we can now talk about what is the electric dipole moment. Electric dipole moment is defined as P equal to the product of the charge and distance of separation. So when we're talking about a dipole system, a dipole is a system made up of 2 charges that have the same magnitude but have opposite signs. So now these 2 charges, one of them, the charge of their charges are equal, so the charge Q and the distance of separation A, the product of that is, of the charge Q and the distance of separation A, gives us what we call dipole moment, which is defined as P. So let's move forward. From the previous slide, we had our E to be, we had our E, which, our E defined as this. And when you look at this QA is what we have just defined to be P. So then moving forward, we can come and replace everything on top of the previous equation. We can, come back here. So we can replace the QA by the dipole moment. And with further simplification, from this, just dividing both terms here by y squared, you have y squared is power 3 over 2 outside the bracket. So these are basic mathematics that you should play with at your leisure time. And E, okay, the only thing I think I should draw your attention to is from this expression, we have used binomial expansion to resolve everything in this bracket to give us this expression. And in summary, when we look at this diagram one more time, the distance between these 2 charges, which we call A, is smaller than the distance P, the distance between the charges to this point P. So that means that the length Y is far greater than A. Just like that, since Y is far greater than A, then we can say that A is very small. So when we are saying A is very small, A that is very small being divided by 2, also being divided by a big number Y, or a big value Y, then everything here will be very, very tiny. And when it's very, very tiny, we can neglect them. We can just assume they are not there at all if the value is tiny. So if it's not there, then it's as good as close to 0. When it's close to 0, the other terms here would also be approximately 0. So when we add all those values that are close to 0 to 1, we have approximately 1. And that leaves us with the formula that says E equal to Kp over Y cubed. So Kp over Y cubed tells us that gives us the relationship between the electric field and the electric dipole. The electric dipole moment, rather. This is the electric field, and this is the electric dipole moment. So let's talk about electric potential. Electric potential, unlike all the major terms we've spoken about electric force, we've spoken about electric field strength or electric field, which are vector quantities. But electric potential is a scalar quantity, meaning that we are only concerned about its magnitude. We are not concerned about direction while discussing electric potential. It's a scalar quantity and can be used to describe the electric field. And it's measured, it is measured in volts. It's measured in volts. So the electric potential can be defined as the amount of work done on a unit charge, or the amount of work done by a unit charge to move it from infinity to a particular point in the field. When we say from infinity, we are meaning from a point that is very far, away from the electric charges. I would say infinity, that is very far away. Doesn't mean from Pluto or Neptune. When it's far away in the sense that the effect of the electric field at that point is negligible. It is not noticed in a region where the electric field is very, very negligible. Then we can say that point is a point at infinity with respect to a particular charge or to a particular field. So when we move a charged object within an electric field, work is either done by the charge or work is done on the charge. Just like we have in gravitational field, where we say a body moves according to following the laws of gravitational field or due to the presence of gravitational field potential. The same way, charge moves in electric field due to electric potentials. So, and when they move when bodies move in gravitational potential, we say they do work or work is done on them. The same way, when charge moves in electric field, with the charged bodies either do work or work is done on them. So a body of mass, just like I've written here, let's read together. A body of mass within the Earth's gravitational field has a potential energy due to its interaction with the Earth. And the potential energy varies with the distance from the center of the Earth. Similarly, a test charge within the electric field of another charge has a potential energy due to Coulomb's interaction between them. And the electric potential energy varies with the distance from the center of the charge producing the field. So that means that just like we calculate the electric field strength or the electric field at a particular point away from a charge, we can also calculate the electric potential at a particular point away from the Earth. And that is defined as the work done on the unit charge to bring that charge from far, far away to that particular point in the electric field. So when we cannot talk about electric potential without talking about work done, because and just like so what we'll be talking about under this electric potential is directly similar to what you have done while discussing gravitational potential. So, WAB, let's call WAB as the work done whenever a test charge moves from A to B. So when the test charge moves from A to B, the work done is WAB. Once it moves from A to B, where A and B are points in the electric field. So electric potential between 2 points A and B is the work done to move a unit charge from point A to B, and the unit is joule per coulomb, or simply volts. Joule per coulomb or volts. So this expression we have here, it's worthy of noting. That is the, we know the SI unit for work to be joule, while that of charge to be coulomb. So we can say the unit is joule per coulomb, and simply volts. And in secondary school physics and what will be seen very soon, we should be able to also say that joule divided by coulomb is equal to volts. Good. So when a body moves from point A to point B, when the potential at point A, is VA, and the potential at point B is VB, and the potential at point A is VA, and the potential at point B is VB, then the work done is can be is WAB when the charge is Q. So the potential difference VB minus VA is as good as the work done divided by the charge. And we can also say that the charge, the product of the charge and the potential difference is the work done to go from point A to B within the field. So work done on the charge when VB is greater than VA is just like pushing a body uphill in the gravitational field, while work done by the charge when VB is greater than, when V is greater than VB, is like rolling a mass downhill. So this, when you are moving uphill, you can say that, or you are doing work. When you are climbing a mountain, you can say you are doing work. But after climbing the mountain, if you decide not to use your legs anymore, you decide to just roll down, we cannot really say you are doing work. We can say work is being done on you. So the same way charges, when a charge body is moving from a point to another, if it does work, moving from point A to point B, then we will say work will be done on it for it to move back from point B back to point A. So when we say a particular charge is at infinity, but we'll say a particular charge is far, far away, then we can say that the potential at that point that is far, far away is zero. So when we now go back to this, our expression, when the body is coming from a point A, which is far, far away, then we can say that the potential VA there will be zero. And easily we can say that the potential B, the potential at B, which is VB, or we can just simplify it to just say V, will be equal to the work done from bringing that charge from infinity divided by that charge itself. So if that charge itself is a unit charge, if that charge is a unit charge, it means that charge has 1 coulomb in value. So if the charge is a unit charge, then we can say that, okay, like I was saying, if the charge is a unit charge, that means Q will be equal to 1. So when Q is 1, then we can now define our potential to be the work done in bringing a unit charge from infinity to that point. So let me say it again. The potential, the electric potential at that point will be the work done to bring a unit charge from infinity to that particular point. So let's continue. So it is convenient to assume that both the charge creating the field and the test charge are positive, so that the lines of force are radially outward. And the electric potential near a positive charge is positive, while that near a negative charge is negative. This implies that zero potential can be obtained in between the positive charge and the negative charge. What this is telling us, when we have a positive charge here and the negative charge here, and like we've said in the past, like we said long ago, that the lines of force for a negative charge is directed radially inwards, while the lines of force in a positive charge is directed radially outwards. When you at a particular point in between the positive and negative charge, that particular charge will not even experience any force, because at that point the two charges will be so balanced such that the charge will not even know if it should okay, let me use another. Let me use a positive, two positive charges. When I have two positive charges, we can have another charge in between, in which this positive charge will be repelling this charge away, while this other one will also be repelling it. So it gets to a point in which it won't even know where to go, either to go to the left or to the right. Then it will decide to stay at a particular point, and at that point it will not experience a net force. The force it's experiencing from the right is equal to that it's experiencing from the left. So the electric potential near a positive charge is positive, while that near a negative charge is negative. So to show that electric potential varies with distance in an electric field, we can apply Coulomb's law. So this is Coulomb's law, which says that if the field is created by the charge Q, the force experienced by the test charge is given by, so the force experienced by when we have a charge Q, the electric field generated by the charge Q can be said to be E. Electric field can be said to be E K, sorry, KQ, charge big Q, sorry, the charge big Q divided by R squared. So when we bring in another test charge small q, recall we said that force, the electric force is also a product of charge and electric field. So we can, when we multiply charge with electric field, we come back to Coulomb's law. So now we are trying to relate work done to electric potential. So the movement of a test charge from a point A to point B can be accomplished by a series of small distances dr. So these small distances dr, we can calculate them in bits, small, just like we're talking about in continuous charges on a line, or continuous charges in a volume and on the surface. So we can cut them into small distances dr, and now calculate the work it will do in moving through those small distances, then we will be talking about this expression, which is work, just like we learned in mechanics. Work is force times distance, right? So when we say work is force times distance, this is the same. But why are we having negative there? The minus sign is because positive dW means negative dr. Positive dW means negative dr. So that means increase in potential energy means decrease in distance. Increase in potential energy means decrease in distance, and vice versa. So the total work done can be obtained via integration. What we had previously was the W equal to F dr. Now we are talking about W itself, not the W. And from integration, so we have to integrate both sides to have W from the W, and which leads to equation 5. And the potential energy between points A and B is given by equation 6. So I suggest at your leisure time, you play around these equations and see how one leads to the other. So if the initial position, point A, of a test charge is at infinity, the absolute potential at point B will be equation 7. I think I've spoken about this earlier. Well, I said at point infinity, that is at point infinity, VA at infinity, or at point far away, where if our point A is at point far away, if A, let me write it a bit. If A is, oh my God, sorry, undo. If A is at infinity, that is if A is far away, then VA will be equal to 0. And from our previous expressions where we spoke about VA minus VB to be equal to WAB over Q. So, and so when VA is 0, then our VB will be left with WAB over Q. So everything we have here is similar to saying WAB over Q. So let's move on. Examples. What positive charge will have an absolute potential plus 100 at 1 centimeter from it? What positive charge will have an absolute potential of plus 100 at 1 centimeter from it? So from the previous examples, we can say that the potential V is equal to KQ divided by R. I will say potential KQ divided by R. Then we can make Q the subject of the formula here to have Q equal to VR divided by K. And our V is 100. Our R is 0.01 meter. And K, 9 times 10 raised power 9. So whatsoever you get here, Coulomb. So, and in this other example is saying how much energy is acquired by an electron in moving through a potential difference 1 volt. How much energy is acquired by an electron in moving through a potential difference 1 volt? That is W equal to QV. W equal to QV. And W is the energy work done, and it's equal to the product of the charge and the potential difference. Product of the what is the charge here? We said an electron. By now, we should know the charge of an electron by heart, even without memorizing it, just by walking around electrons. That is 1.6 times 10 raised power minus 19 Coulomb times 1 volt. So when we multiply 1.6 times 10 power minus 19 Coulomb by 1 volt, we should get 1.6 times 10 raised power minus 19 joules. So product of Coulomb and volts is joules. I think I said something similar to that earlier. So these are just simple examples. So let's move further. Coulomb's force F and the electric field strength E are both vectors and related by this expression. We have dealt with this over and over. The work done by a force in moving its point of application through a distance dr between points A and B is WAB, which is just force times distance, like you said earlier, and that the potential difference VA minus VB equal to W over Q. We said this also earlier. The simple relationship between potential difference and electric field strength is therefore VB minus VA equal to E dr. VB minus VA equal to E dr. And our E is equal to the potential difference divided by the change in distance. The potential difference divided by the change in distance. So let's move further. In the general case, the field may not be uniform, and the paths may not be along a straight line between A and B. It may be along any contour length. The work done is WAB, just like we have in equation 10, minus Q integral E dl. So, and the absolute potential at the point B can be related to the electric field strength as VB equal to minus integral E dl. That is when we are talking about absolute potential, we mean that the other potential is at the other point is at infinity, which means the potential of the other point is 0. So we should also be mindful of the direction of the force, minus QE. Doing the work, if the force of the field is QE. So now let's talk about potential gradients. The space rate of change of a quantity in the direction of increase is defined as gradients. Potential gradient in electricity is analogous to the gradients of an inclined plane, just like the gradients when you are plotting a graph in mechanics or temperature gradients. Different areas of physics we talk about gradients, and the same thing applies when we are talking about potential gradients. The change of that potential with respect to distance. So the potential gradient is the rate of change of potential with distance along the line of force. So that is change of potential divided by change of distance, and the unit is volts per meter. So let's take, for example, two parallel plates separated by a distance 0.5 meter. When one is maintained at the potential of 100 volts above the other, the potential gradient is 200 volts per meter. So here the potential difference is 100 and the distance is 0.5. So 100 divided by 0.5 will give you 200 volts per meter. Let's move forward. The relationship between the potential gradient and electric field and work done is given in equation 13. So this is equation 13, which connects the electric field, the work done, and the potential gradients. The potential gradient. So, okay, this is change of potential, change of work over Q. So we can have, from this 13, we can have 14 easily by replacing, by replacing delta W with QV, Q dV. So from this expression, delta W Q dV, and that gives us equal to minus QE dx, and Q we cancel Q, and E will be left with E, which is equal to delta V over delta X, and the minus would apply. So the electric field intensity at a point is equal to the negative potential gradient of the field at that point. The electric field intensity at a point is equal to the negative potential gradient. The delta V over everything we have here is potential gradients. So we can see directly here that the electric field intensity is just like a negative of potential gradients. So the stories we have here is just equation 14 in English. So let's quickly talk about electric potential energy. Electric potential at a point which is at a distance RB from the charge Q creating the Coulomb field is given in equation 15. But this should be electric potential. This should be electric potential energy. The electric potential energy is given in equation 15. So we assuming Q is positive and another positive Q is brought from infinity to this point, then the work done is Q VB. This is stored as the electric potential energy U of the system of two charges, and that gives us equation 15. So we've spoken about different expressions. We've spoken about the expressions for electric force. We've spoken about that of electric field, that of electric potential, that of potential gradients. Now we are talking about electric potential energy. It's good we go over this note again and find the balance for each of them. So we can have a system containing more than two charges. When the expression we had in equation 15 is just talking about two charges. But what if there are more than two charges and we want to know what is the potential energy? How that is done is to calculate for each pair. So when we have we have in equation 4 has been expanded for a system of 4 charges. So when we have Q1, Q2, Q3, Q4, it can be anywhere. Don't let me put it too orderly. And when we have Q4, we are going to use that equation 15. We'll start by calculating what is the potential energy between Q1. Okay, let's start with Q1 and Q2. Then we go to Q1 and Q3. Then we go to Q1 and Q4. Then we return to say, what is that of Q2 and Q3? We know we have done for Q1 and Q2, so there is no need for saying Q2 and Q1 anymore. So Q2 and Q3, and then Q2 and Q4. Then we come to number 3. I will say Q3 and Q4. We don't have to think about 1 and 2 anymore, because while talking about Q1 and Q3, we have resolved Q1 and Q3. There is no point going for Q3 and Q1, having done Q1 and Q3. That would be double counting. So from this expression, it simply tells us that the distance between Q1 and Q2 is R12. Distance between Q1 and Q3 is R13. Distance between Q1 and Q4 is R14. Distance between Q2 and Q3 is R23. Between Q2 and Q4 is R24. Distance between Q3 and Q4 is R34. So the distance between both of them is important it's important in determining the electric potential energy of the system of more than two charges. So the electric field energy, the electric potential energy may be either positive or negative. So in this scenario, unlike what we find, it's a potential energy, but when we are calculating the potential energy of a positive and a negative charge, they should multiply it to give us a negative value. When they are like charges, positive and positive, they will multiply to give a positive value, and when they are both negatives, they multiply to give negative values. But when they are opposite charges, so most times in physics, when we hear that the potential energy is in a system of electric charges, when we hear that it's positive, we know that such charge is a repulsive, nature, that the parties involved are repulsive to each other. But when the potential energy is negative, we know that that's attractive in nature. So let's move forward. Okay, these are examples. 2 protons in the nucleus are separated by a distance 6 times 10 raised to a minus 15 meter. What is their mutual potential energy? What is their mutual potential energy? Just like we have in this expression that says U equal to K Q1 Q2 over R. We come here again to say the potential energy U. Let me use a brighter color. U K Q1 Q2 over R. And we know our Q1 and Q2 to be protons. And that means that our K times 1.6 times 10 raised to power minus 19 coulomb times 1.6 times 10 raised to power minus 19 coulomb. So if it were to be an electron were to be involved, we would have introduced the minus while talking about the 1.6 times 10 raised to power minus 19 coulomb. So I should have, let me erase the column I put here to remove myself. So all divided by the distance. The distance is 6 times 10 raised to power minus 15 meter. So they would multiply up with K to give us a unit of joule. So whatsoever you get is correct. But sometimes it is also a convenience to talk about sometimes it's convenient to talk about these energies in terms of electron volts. So whatsoever we get here, we divide by 1.6 times 10 raised to power minus 19, because one electron volt is 1.6 times 10 raised to power minus 19 joules. So sometimes you may want your values in electron volts, which is sometimes very convenient, because when you are dealing with values of this order of 10 raised to power minus 19, you may not really know which is big or which is small. But when you work in the order of electron volts, you'll be able to determine to say, wow, this is a very high value and this is a small value. So we also have another example here that says 3 identical charges of 15 microcoulomb each are located on the vertices of an equilateral triangle. So I think we should start by drawing an equilateral triangle. There are 3 charges, 15 microcoulomb, 15, why is this 15 looking like it? 15 microcoulomb and 15 microcoulomb. Calculate the look at the vertices of that triangle. That is 9 cm in each side, 9 cm in each side. So 0.09 meter, 0.09 meter. So we can go ahead to knowing that microcoulomb is 10 raised to power minus 6 coulomb. So from there we can come to say that our potential energy U will be K 15 times 15 times 10 raised to power minus 12 divided by 0.09, and we'll do this for Q1 and Q2, Q1 and Q3, and Q2 and Q3. So it's as good as we multiplying everything here by 3. Or when you do it, when you take this, we will have the same thing we will do for Q1 and Q2. We will have the same for Q2 and Q3, and we'll also have the same value for Q3 and Q4, since they are all identical charges. They are all positive charges, and they are all equally distributed. So easily we can say the potential energy will be between a particular pair will be the same for all other pairs, and that will give us this value for potential energy. So I think we are at the time is up. So in the next class, which will be next Monday, we'll be talking about capacitors and dielectrics. Please, if you have questions that I have not attended to, please send me an email through physics104@stu.ui.edu.ng. And there are books that are recommended. Let me see if I have money. there are books that are recommended that is also on the LMS page. And we have one written by our professors in the department here. It's Fundamentals of Electricity and Magnetism. So I suggest you get it. I think it should be available in the bookshop, but I'm not sure. But if you can't get it, let me know. I would get back to you on it. So it's one of the course materials I use as well, and I recommend it to you. And I expect you to also use every channel of communication to maximize your understanding of this course. So see you on Monday.